Hello, hello. Are we all here? Hello. Oh, okay. Hello. Good afternoon. All right. Let's good. Oh yeah. Okay. Wait, let's see. Okay. Good afternoon, Christopher. Because that's video. Good afternoon, many people. Good afternoon, Yavi. Good afternoon, Melita. Good afternoon, Amanda. Mendez. Awesome. I like the Yaverbound. I mean, that's my name. Good afternoon, Avani. Good afternoon, Yeyun. Good afternoon, Hayu. Good afternoon, Matthew. Good afternoon, Michelle. Oh, there's Cheska, and there's Michelle. Awesome. Hello from the other side. Yeah, I don't know which side, but all right, fair enough. Hello to you too. Good afternoon, Marilyn. Good afternoon, Giselle. Awesome. All right. Major shout outs to Christopher, Cheska, and Michelle. Of course, I'm just saying. And oh, did I say? And Michelle. Michelle. Okay, this is the first day I'm realizing we have two Michelles. I'm so okay, right. But thank you, Michelle, for the avatar, and thank you, Michelle, for the video, or the other way around. All right. Good afternoon, Giselle. If I didn't say that, how did I not know that until today? All right, that's ridiculous. Okay, I will be more conscious of that in the future. Okay. So we have things to do. So to be clear, yeah. So this week just to be clear, this week we're flipping. Last week, you guys didn't have class synchronously. You watched the video from the other class. Thank you very much. Everybody was very, I think, attentive and did the right thing about that. So thank you. So just to be clear, this Wednesday, you do have synchronous class at 3:05. The other class will watch your video. Not that you care, but just to be clear, we do have class on this. Then, of course, you don't have school on Monday. Okay, why am I bringing all that up? Because I feel that people are doing well trying to keep up with the homework. Obviously, it's getting harder and harder now. That's what happens. But I think more and more people are understanding that it's just an ongoing back and forth between you and me, draft, revision, whatever. It still remains the case that anybody in this room could still get any and all points that they want on any of the assignments. It is not too late for any of that. And it's not too late for me to give you feedback on any assignments that I still owe you feedback on, et cetera, et cetera. I think you're all getting that. But therefore, the very next assignment has been posted, homework 7, definitely another leap forward, definitely bigger, thicker, new subtopic. That new assignment that was posted, assignment 7, is due a week from this Wednesday. Just to be, I think I did that right in Google Classroom. Just to be clear, like it's not due in 2 days and it's not due in a week. It's due in a week and 2 days. So hope. And during that time, you can and should also catch up on anything else you want to catch up on leading to that, for whatever that's worth. I'm also bringing that up to say, this might be a little bit unclear to people. Last time we had some sort of class, like last video class, I was in the midst of going over homework 6, the big old duck assignment, within which things are starting to get thicker. We're getting into constant acceleration now. Constant acceleration is a central topic in physics. It follows from the topic constant velocity, but it's harder and it's deeper and it's easy to confuse with constant velocity, but it is its own thing. That's what we're involved in right now. And the thing I'm trying to say is, we were in the middle of going over homework 6 when last I spoke to anybody. We will continue going over homework 6. We're not done with it. There's definitely more to be said about it and more to be clarified about it, but that's not going to happen today. That's really what I'm trying to make clear here today. That will happen in the next class. In the next class, we'll go back to homework 6, which also secretly means, we probably are not going to get very far into homework 7 in the last class. So take that information any way you want. But it means if you don't finish everything the night before, you still might have some time. But anyway, we will get to homework 6 the next class. We'll get back to homework 6, the next class. Let me say that again. We're not done with homework 6. There's a lot more to be said about it and a lot more answers to walk through. In fact, I should be really clear too. I've now, graded many people's homework 6 or looked through it, and it's pretty clear to me that the one problem that I talked about in the last video, the one problem of a ball rolling down a 3-foot incline, like it's like I think it's problem 2 in Roman numeral 2 or something, but there's a ball rolling down a 3-foot incline or 6-foot incline, and it takes 2 seconds to roll down the 6-foot incline. And it's like simple problem, but it's not an easy problem. And it's just simple enough that it's one of those problems where a lot of people did it and did it straightforwardly, maybe even did it confidently, but a lot of people got the wrong answer to part B of it, where it asks, how far does it get in the first second? So I just want to emphasize that now that I've looked through a lot of homeworks there, indeed, if you haven't watched that part of the video, or if you haven't thought about that problem where a ball rolls down a 6-foot incline in 2 seconds, that's like a very central, like you'll kind of know whether you're knowing what's going on or not if you look carefully at that problem and look at the correct solution, which is that the problem travels 1.5 feet in the first second. It doesn't travel 3 feet in the first second. So I'm just saying, I've now looked, and I think a lot of people hopefully either did or will benefit from that discussion. Okay. But then there's a lot of other problems in homework 6 that we have not yet gone over. We will not today, because today what we're going to do is go back to something that you thought hard about many, many nights ago, but we've never discussed yet, which is homework 3. Like as promised, the one thing we've never dealt with yet, but we must, is homework 3, train of thought. So that's what we're doing today. Again, if there's any confusion, let me know in the chat. But today is all about homework 3, train of thought. We're going to eventually, by the end of today, establish 3, like an important conclusion that comes from train of thought. We need that conclusion for the rest of this class and for all of physics 204. Like it'll never go away. In fact, to give you a sneak preview or whatever, we're going to establish a principle that is said many different ways. We're going to establish a principle today that has many different forms, as you can tell from the screen right now. There's one principle that we're going to establish by the end of today's class, but it is expressed many, many different ways. We're going to express it 3 different ways today. There are more ways to come throughout the rest of this semester. There's like 6 more ways to come, just so you understand this. So it's important. It's conceptual. It doesn't yet look mathematical, but it becomes mathematical. We're going to see 9 different ways to express a certain principle. That's what needs to be established by the end of today. Again, this is a longer intro than I mean. What I want to make clear is we need this principle for the rest of physics, for all time in physics, but we're only going to explicitly talk about homework 3 once today. Like when today is over, then we're done explicitly going over that homework. And we'll move back to homework 6 and keep going in order from then. I hope that's not confusing, or if it is, please let me know in the chat. But what I'm trying to say is now, for one day only, we're going to turn our attention explicitly to homework 3. So I'm actually going to change the screen share for a little bit. Hold on, bear with me. Oh, I'm glad, and welcome Melita also. Oh, wait, sorry. And welcome also Yiyun. Good to see you. Very good to see you. Okay, I'm switching the screen share. Bear with me for a second. Yes. Okay, here we go. Oh, come on. Okay. All right. So I would highly suggest that you have your own copy of this in front of you, and even better than that, have your own copy of your answers to this, because I know it was a while ago that you thought about it. And we're going to make this a little bit of a discussion, but a lot of me talking. All right, so here's the scenario, right? So you see it on your screen. Yes, yes, yes. Okay. So this is the train of thought. This, and you may want to make a note of this. This is what is known in physics as a thought experiment, or more properly, more technically in physics, this is known as a Gedanken experiment. GEDANKEN, Gedanken experiment. Gedanken means thought in German. That's my understanding. So this is a thought experiment. Thought experiments are very real and important in physics. A thought experiment is something that you can run in your mind. It only works if you assume that, if we assume that most reasonable people, after a certain amount of discussion, would come to similar conclusions about what they see in their mind. So all of physics can't be done in the mind, obviously, but a lot of important conclusions, or at least ways of thinking in physics, start as thought experiments. And Einstein in particular was very famous for very groundbreaking thought experiments that he developed and ran in his mind, and then got other people to see that it wasn't only his mind that would observe certain conclusions, but that everybody would agree with the conclusions once he set them up a certain way. So they're very fundamental in physics. This thought experiment, as you read, is a scenario where it's like late on an exhausting school night. You wake up to find yourself sitting in the car of a sleek and modern express subway train. So as you all read to yourselves weeks ago, the whole idea is that the train is optimized, right? This is not supposed to be this is not supposed to be a total fantasy train. It's supposed to be sort of an idealized, dreamy-like version of the kinds of trains that you're used to being in. Like, maybe this is not the C train, maybe this is the A train, which is a little bit more of a modern train, right? And or maybe, if better, this is a train in Tokyo or Washington, D.C., or something like that, where the technology is very slick, where you don't feel the bumps and lurches that much, where, as I think many of you would agree with, like the A train, where all the seats are facing all various directions on purpose, so that, the front of the train could be the back, or the back could be the front, right? I mean, I think everybody's familiar with that. And so you find yourself in one of these trains, and there's nothing particular, there's no sensory evidence that particularly indicates whether you're going in a particular direction or at a particular speed, or if you're moving in particular at all, right? That's the scenario. And it's a scenario. It's hypothetical, but it's not meant to be preposterous. Wait, there's something in the chat. Oh, thank you. Okay, thank you, Amanda. I totally appreciate it. Okay, great. Okay. All right. So the fundamental question of the whole thing, the question that you're asked over and over again is, are you moving? Like, based on the evidence that you have in front of you, and let's assume you just woke up, like you were napping and now you just woke up, so you don't know if you fell asleep at a station or midway between stations. Or, by the way, I should even add, maybe you just woke up and you're in such a dreamy sleep-like state, or perhaps even an artificially induced state because it's Saturday night, I don't know, but you're in such a state that you're not even sure if you literally just woke up out of a dream, or maybe now you're like waking into a dream. It's just not 100% clear. And so you don't know. And it's all dark outside the windows, of course, because it's a subway. So you don't literally, obviously know whether you're moving or not. So the question is posed, are you moving? Okay. And you're asked to sketch the whole train, which I appreciate that people did, and some people did with more care than others, but we won't go into all that right now. But then various iterations of the question, are you moving, are asked of you. Different ways of you're asked that question in all kinds of different ways. And you're even given this option, oh, do I not have enough information to answer this question, right? But then if you go through the packet, as you all know, eventually you're given more and more information, right? Eventually you see these white lights, so maybe that indicates something, or maybe it doesn't. Things happen that give you more information. What I want to focus on right now is just the fundamental first question that is asked before any extra information is provided. The first question, question 1B, like after the sketches, is at this moment, are you moving? Now, the first thing I'm going to turn it to you guys. I want you to remember or be referring to what you wrote. I want to know honestly, and at this point, there's no right or wrong answers, really. I want to know honestly what either you put, if you recall, or what you would put right now, just at this stage of the packet. So we're going to take informal votes here, like in Zoom. We're going to take informal votes. I'm going to tell you right now, the only thing you can do wrong is not answer at all. And I will be a little bit of a jerk about that. I want everybody to commit to exactly one out of the 5 options. Like the question we're looking at is the one on the screen. It says, at this moment, are you moving? There are 5 options. Some of them are very similar. It's in your mind, you distinguish, like, I think there's differences among all those 5, but what exactly the differences are, that's up to you to decide. But I want an answer for everybody in a moment. The first thing I want to do is no. Okay, there's 15 of us if you don't count me and you don't count my board. There's 15 of us. So the first thing I want is, as a control to this experiment, raise your electronic hand right now if you hear me talking at all. If you're in the room, thank you, awesome. Keep them up. This is a control. Thank you. Keep them up. That's 11. 12. I'm going to wait till I have 15. I want to do this right. Keep your hands up, please. I want you to 13. Awesome. We're almost there. I believe there's a total of 15 of you. Wait, keep them up. Thank you. Keep them up, because there's 3. I believe there's 13 of you raising your hands. I believe there's 15 of you in the room. I want to see everybody. This is a synchronous class. I want to see everybody affirm that you are here right now. And I'm not going to mention names, except I might. We have 14. There's one person. Amanda, are you there? I'm not trying to embarrass anybody or single anybody out, but Amanda, are you there? All right, I'm not going to sing. All right, we're going to go with, all right, our population right now, our statistical sample is 14. Thank you. Okay, thank you. I appreciate that. I didn't want to make that any more awkward than I already did. Okay, so that's 15 people. We got 15 people in the room. Great. So now we're going to take a vote. I don't care what you vote, but I care that you vote exactly once. This is like a group effort here. So yeah, you can put your hands down now. Thank you very much. So here we go. Awesome. As soon as all the hands are down, awesome. We are going to, okay. So here's the question, right? Based on the evidence supplied, are you moving? Raise your hand for option A, yes. Like raise your hand if you said, or you're saying yes. Raise your hand now. Going once. I'm going to say it again. That's 1. I'm not mentioning names. I don't care about names. There's 1. So 1 person said yes. Okay, interesting. All right, fair. Remember, I don't care, but I want these all to add up to 15. So that's 1. All right, 1 person said yes, I am moving. Raise your hand for no, I am not moving. That's 2. That's 3. That's 5. Oh, wow, that's a lot. Wow. That's 7, 8. Okay, 8 people are saying no, not moving. So we got 1 for yes. We've got 8 for no. That's interesting. That's quite a disparity. And I'll tell you what the other class did in a minute too, just so you, for whatever data or, okay, you can put your hands down. Thank you. So that was 1 vote for yes. That was, I believe, 8. I just forgot, but I think it was 8 votes for no. Now, for both yes and, Melita, are you raising your, I'm sorry to mention names. Melita, are you, okay, so we're doing both yes and no. We're doing the third option, option C, both yes and no. How many people are voting for that? We have 2 for both yes and no. 3 for both yes and no. We have 3. Yes, going once. So I believe that so far for yes, I think we had 8. I think. Tell me if I'm wrong in the chat. For no, we had 1. That's 9. For this, we have 3. That's 12. Okay, you can put your hands down. Okay, now for neither yes nor no. Like neither one is the answer. Going once, okay, 1 person. Okay, so neither yes nor no, 1 person. Awesome, fine, great, thank you. And you can put your hand down now. So that makes 13, I believe. And now finally, E, not enough information to choose any of the above. Put your hand up for E. 1. Okay, 1. That either adds up to 14 or 15. I'm going to be generous and assume that adds up to 15 because I lost track of one somewhere along the way. But all right, we got one for E. Okay, you could put, thank you. You could put your hand down. Okay, I think everybody voted. There's maybe one person didn't, but I think everybody voted. Okay, I'm going to say a couple of things. First of all, one thing that's just sort of interesting is your answers were very different from the other sections. And I mean, it doesn't matter. I mean, this was like weeks ago when anybody barely knew anybody. And I don't think I had done anything very different in the two classes at that point. Just so you know, like in the other section, nobody voted for D whatsoever. Like nobody voted for D, but there was almost a 50-50 split between yes and no. It was like 6 and 6 on yes and no. And about 4 people voted for not enough information. Only one person voted for that here. And I forgot the other. So, I mean, I would say, I mean, there's a huge distribution here. It seems like the overwhelming majority of you did put yes, or the overwhelming plurality of you put yes, but that's in this section, just so you know, something very different happened in the other section. So the first thing I just want to say is that I think reasonable minds can differ about this. I think we could have a whole discussion for hours about everybody's reasons. And I'm sure I would find everybody's reasons very compelling. I think answers can be all over the map here, legitimately. Now, that doesn't mean this is all just a matter of feelings. Like I am going to get somewhere with this, that we are going to get to a conclusion. But first and foremost, I do think, even though this is a very simple question, are you moving? I mean, everything in physics is about motion, right? Everything assumes some definition or concept of motion. And here we have like a very simple scenario. You're in a train. It's a pretty slick train. And just forget about numbers, forget about actual velocities or average velocities or instantaneous velocities or accelerations. We're just asking, are you moving at all? We're just asking, is there any velocity? And it's a little bit unclear, even in this scenario, right? And answers are all over the board. Oh, wait, there's something in the chat. Hold on. Oh, wait. Oh, did I say it backwards? I'm sorry. Thank you, Michelle. Wait, I said it. Oh, sorry. You're absolutely right. I totally said it backwards. Thank you. No, and I'm glad you're paying attention. And I do want the input, I should say, especially with today. This is so conceptual. Yes, thank you for the input. You're right. I said it backwards. A lot of people voted no, not yes. In the other class, it was split down the middle between yes and no. And in the other class, a lot of people voted for not enough information. But yes, you're right. I said it backwards. Thank you. Okay, cool. Definitely submit that for points. And I'm going to say, I meant to say this too. This is not just going to be a matter of opinions. We're going to actually get to a conclusion with all this today, but it is conceptual. This is what we're trying to discuss here is the foundation of physics. Like this comes you were assigned this before you were assigned a lot of math. That's on purpose. We didn't start discussing it until now after you've done some math. That's also on purpose. But this conceptual content of physics is arguably what distinguishes physics from pure math. Like physics is not the same as math. Physics ends up looking a lot like math, and the language of physics is math. But at the core, physics is about motion through space and time. And we use math to describe motion through space and time. At its core, physics is about concepts that we must match to our intuition in order to use them. And arguably, ideally, should originally stem from our intuition in order to use them. That is, physics can get very elaborate. It can look very sophisticated and very detailed and can get very challenging. But at its core, it is supposed to begin and end with things that make sense. Physics is an attempt to make sense out of the universe and out of space and time. Therefore, what I'm trying to say is today is going to be very conceptual. That doesn't mean it's haphazard or anarchic. It just means it's conceptual. So I'm actually glad that Michelle already put something in the chat. At any moment, if I say anything that anybody wants to debate or question or a challenge, you definitely should, even and especially those of you who sometimes maybe don't feel qualified to get into a detailed discussion about something mathematical, because some of you might not feel qualified when it comes to sophisticated mathematics. I think that's a feeling. I mean, I think you should feel qualified, but I understand if you don't. But here, everybody knows about trains. Everybody's been on trains. Everybody has something to say about this. And that's partly why we just started with a vote like that, because this is the way physics is supposed to begin and end. It's supposed to begin and end with a gut check of what in my gut do I actually think is going on in the world. So we started here with a gut check of whether intuitively we feel that we're moving or not. Okay, but we came to all these different answers. Okay, so how do we reconcile them? I'm gonna drop the screen share now for a while. Hold on. Yeah, I'm gonna drop the screen share for a while. Okay. We just came to all these different answers. So we have to reconcile them. Before I reconcile them, I want to ask one more vote. I want to take one more vote. I want to say this. This is a thought experiment. This is hypothetical. It's imaginary, right? It's imaginary because it's sort of optimized, because it's supposed to be a very slick subway. It's supposed to be like most of the normal imperfections of daily life are supposed to be vanishingly small in this scenario. But before we go any further, I want to check something with you. I want to see you raise an electronic hand if ever in your actual life, if even for a moment you have ever experienced this kind of confusion where even for a moment you weren't sure if something was moving past you or you were moving past something else. Okay, already I see Chris, thank you. And is Chris the only one? I mean, I'll repeat the question, or a lot of, okay, Marilyn, thank you. Michelle, Freddie, Matthew, thank you. Melita, I think I saw Melita. Amanda, Giselle, thank you. Right, so there, thank you. Right, there, right, and I'm gonna turn it to them or any of you in a second to elaborate. But I just want to establish at least half of you in the room are at least half of you are claiming that this thought experiment, this hypothetical, is not totally far-fetched. Like, it's actually based on something that could ever possibly happen in someone's life, even for a moment. I'm going to stop right there. Okay, hold on one second. Hold on. I'm going to stop. Okay, I'm going to stop right now to ask if any of the people, whether it's Melita or Amanda or Chris or anybody, could you just elaborate for a moment, like just share with the rest of the class the type of scenario you're thinking of that you've ever been in, where even for a moment you were confused. Melita, yes, and then Michelle. And for this, definitely, by the way, anybody who wants to say anything, please do. Like, we should call on anybody. I don't even care if it seems redundant or what. Like, I definitely want to hear. So yeah, who did I just say first? Was it Melita? Okay, I think it was Melita.
I think like falling asleep on the bus when you're going somewhere, like you wake up and like you're like, wait, where am I?
Okay, and I totally agree. It certainly happens to me. And can I just qualify or clarify for a second? When you say you wake up and you're like, where am I? Totally agree. Can we also add, is it also part of what you're saying that you're like, wait, like, am I moving or not? Like, is that part of
Yeah.
what?
Yeah, like especially if you're like going through one of the tunnels or something, and then you have like no clue where you are.
Awesome. Okay. And tunnel makes it that much more vivid. Absolutely. Okay, so cool. So we got Melita. I'm just taking that to mean, and I'm going to hear the other people too. I'm just taking it to mean that Melita is one person with one example who is saying, okay, this is a hypothetical, but it's not crazy. I mean, that's how I'm taking that to mean. Okay, next was, I think, Amanda, maybe, or Michelle. Michelle, I'm sorry. Yeah. Okay.
I remember as a kid a lot, like while my mom was driving the car, wondering if like the moon was moving or I was.
Oh, I didn't see that one coming. Okay, that's great. I want to hold that. Sorry, not to overreact, but I didn't actually expect you to say that. But I totally agree. That is a fantastic example. And as was as was Melita. So we've been in buses and had this experience. Michelle's saying that she's been in a car and had the experience. And with the bus, it's like relative to a tunnel or something like that. With the car, Michelle's example is like not even necessarily about other cars, but like something in the sky and whether it's moving or not. Awesome example. Keep going. I think did Chris, did you have your hand up?
Yeah, I did.
Okay.
So I said it was like the same situation, but like when you're driving, the clouds are like determine if the clouds are moving or not.
Oh, yes. Oh, and I see in the chat now. I missed the chat. Yes, absolutely. And then I also see Ivani's awesome. Yes, and Ivani also was talking about the moon. It's so cool that you guys can do like the like thing in the middle of Zoom. That's so hilarious to me. But yes, so Ivani's thinking about the moon. So Chris is, yes, about the clouds. And the clouds, well, I want to say more about the clouds and the moon in a couple of minutes, but absolutely. And the clouds are a really good example. I guess I will elaborate for a moment on the cloud thing. The thing that's also interesting, all of these examples are profound, and I do agree with all of them, and they are different. They actually are a variety of examples. Like one thing about the clouds is, we all know clouds actually, I shouldn't say actually, I should never say the word actually, but clouds do move. Right? Like you really can be confused. I mean, the moon, whatever the moon is doing is like a global confusion. Like it's very legitimate to be confused about what the moon's doing, but it's sort of like once you sort it out, maybe, or once an adult tells you or something, whatever answer you ever come to about the moon, maybe then you sort of think that answer is always true. I don't know. Actually, I'm speculating, but like I know my kids often ask about the moon, but then if they they either accept what I'm telling them or they don't accept what I'm telling them. But if they do accept what I'm telling them, then they kind of don't ask again the next time because like the moon just sort of seems like it's always the moon. But with clouds, like some days clouds are sitting there in the sky compared to say a tree. And other days, clouds really are moving. I shouldn't say really, but other days, like you see a cloud moving past a tree. So it really can be confusing with the clouds, what they're doing or not. So anyway, I'm going too far, but yes, totally agree with that, Chris. Who else? Someone else, either is Amanda or Yiyun or both had their hand up. Amanda, did you want to add? Oh, that's scary. Oh, and I'm looking in the chat still. Oh, well, actually, I'm reading the chat. Okay. By the way, so in the chat, and I don't mean to be skipping anybody. I don't want to skip anybody. If anybody has anything to say on this topic, even if you think it's redundant, I don't care. I want to hear it. But so don't give up with the hands or whatever. But in the chat, I'm seeing Michelle Q. I'm gonna have to start doing something about the Michelles here. It's great that both Michelles do participate too. I do appreciate that. Michelle F a minute ago said things about now I just wait about not the tunnel. Oh, the moon, right. Michelle F was talking about the moon, and then Michelle Q is bringing up the issue of an airplane, and an airplane is yet another issue. Now, some of you might be thinking, well, these are all really the same. I mean, whatever. Maybe some of you were thinking it's like green eggs and ham. Like, would you eat them in a plane? Would you eat them in a train? Would you eat them in a box? Would you eat them with a fox? Like, kind of yes, but also kind of no. I think there is something different about each one of these examples that makes it either more or less vivid or memorable or confusing or whatever. Like planes, oh my God, don't get me started about airplanes. I will get started about airplanes at some point. I mean, airplanes, well, one thing, airplanes go really freaking fast, right? I mean, they go really fast and they go really high. And you get in a plane, you'd think your experience would be even more scary and more bizarre and more freakish than in like a car on the highway, right? Because I mean, a plane is going so much faster. You'd think that you'd have to adjust your behavior and your expectations and your responses in an airplane way more than you adjust in a car. But in an airplane, like for the majority of the journey, they tell you it's safe to unbuckle your seatbelts and move freely about the cabin. Like my mother never lets me unbuckle my seatbelt at any speed in a car or even on a local road or pulling out of the driveway. But in an airplane, once you achieve cruising speed and cruising altitude, which I might add is like 600 miles per hour, then you can take off your seatbelt and walk freely about the cabin. And by the way, have you ever noticed on an airplane, if someone says, pass the peanuts, you don't go like this. All right, here we go. Okay, here come, get ready for the pitch like that. Like, right, you're just like, ugh. You know what I'm saying? Like and if you sit back and you start watching a movie on the airplane and like you complain if it's a bad movie, as though you're just like sitting around in a hotel room, like with HBO or like you're going 500 miles per hour. Why are you watching a movie? Like, right? I'm saying something about an airplane, even when you know you're moving, in no way do you know that you're moving. In no way do you behave as though you're moving. If you were, and if you did, you'd never get on the damn thing, if I'm making any sense, right? And last example, on an airplane, if you do walk to the bathroom or something, like, you know, you get up and you start walking to the back, and you use a bathroom, I mean, what? But as you're walking back, I don't know if you, like, I have 2 sons. Okay, we won't go into that. But like, have you ever been tempted while you're walking in an airplane, if you were like little, maybe to like jump up and see what happens? If you jump up on an airplane, the back of the plane does not slam you in the butt. You know what I'm saying? Right? But shouldn't it? If it's going 500 miles an hour, you know what I'm saying? Like, so airplane, definitely a vivid example. Sorry, I'm getting a little crazy. Especially when you fly over the ocean, right? Okay, when you look at it when you're on a plane. Okay, sorry, I'm back to the chat. I'm going a little crazy, but this is what. By the way, if I do go too crazy today or I get too excited, I get very excited about this concept. I will always get very excited about this concept because it's not just an empty, weird concept. Well, I'm going to get back to the chat and back to your comments, but one of the reasons I want to hear these comments and here in the chat is I want to establish right now, before we go any further, that this whole idea of being confused about whether you're moving or not is not it's not like a dumb confusion. It isn't a confusion that's only experienced by little children or people on drugs or people dreaming. It's not a delusion. It's a legitimate confusion. And it's not like, if you just knew a little bit of science, you could resolve this confusion. It's more like all of science, or at least physics, comes out of a huge, deliberate attempt to resolve this confusion. That I'm just trying to get that this is not outside of science. This is actually where science begins, or at least physics. Where physics begins is an attempt on the part of scholarly, thinking, careful, sober people to try to actually get to the bottom of how it is that we can be confused about something as simple as motion. Okay, so it's not like this is every time I get off on a tangent here today, I just want to make it clear it's not a tangent. It's actually the foundation of physics, is the question of whether we are moving or not. And unless we have something specific to say about the question, are we moving or not, then all of our math of velocities and accelerations and all these equations, they're all nonsense if they're all referring to motions that we can't even ascertain in our mind whether they're going on or not. Okay, so that's the context here. So I'm going to go back to the chat, and I'll go back to anybody else, but back to the chat. When moving on a hill in a car. Oh, sorry, I'm looking at Marilyn's. When moving like on a hill in a car would move next to me, and I would get scared if I'm moving backwards. Totally. I mean, I don't know about anybody else. I totally know what Marilyn's talking about. I mean, not everybody in the room necessarily drives, but if you drive, like if you're from Long Island or whatever, if you actually drive, right? Oh my God. And if you're on a hill, exactly, and you're next to a truck, or you're caught in traffic, and then you like space out, and you see the truck next to you start to glide backwards or go, roll forwards. It's totally possible to think for a second, oh my God, did I release my foot from the brake? Like, oh my God, right? Or, I'm elaborating on Marilyn's example, but I totally can relate to Marilyn's example. And I want to say again, if I'm going a little crazy here, I want to say again, it might sound like we're indulging in craziness, but actually one of the lessons by the end of today is meant to be, if you never engage in this confusion, if you never wonder whether you're actually moving or not, then you're truly crazy. I mean, I shouldn't say that so lightly, but it's not crazy to wonder about this. It's crazy not to wonder about it. And furthermore, even in Marilyn's example, like say, she's on a hill, she's on a hill, and then this thing next to her starts moving. So she's like, oh my God, wait, is that thing moving and I'm still, or is that thing still and I'm moving? Even when she then resolves it in her mind, even the one thing to ask yourself is, even if Marilyn only experienced that confusion like for a moment or a minute, and then somehow she worked it out in her mind, and she's like, oh, okay, no, I'm good, I'm doing the right thing. One still has to ask oneself, how did she resolve it exactly? Like, if she was capable of being confused for a moment or capable of coming to the wrong conclusion, how do we actually know that the conclusion that she eventually came to and relied on, what exactly is our proof that that's right? and I will resolve this. I'm not just speculating for fun, although it is fun for me. But okay, and I agree with what Chris is saying. Like there's something legitimately real underlying this issue of whether we're moving or not. And by the one, I know I'm so defensive. I'm like a used car salesman for physics, I know, but I'm just going to say this too. If you're thinking at all like, well, yeah, this is kind of interesting. Like, yeah, I do remember experiencing that when I was 11, but like I grew up and like now I'd like to do some real science. Thank you. Like, I'm here to say like, if this is ever a real question, where else could it be probed besides a physics class? Like physics is the study of motion. So if physicists can't resolve the simple question of are we moving or not, then all the rest of physics is like balancing on a very fragile fulcrum, right? So we're not going to, I promise you we'll get back to all the math and everything like that in homework 6 next week. But if we don't spend one day actually engaging in this question, somehow all the math is kind of just floating out there. So, okay, I'm still in the chat. I definitely agree. Okay, Michelle, thank you. She definitely agrees, especially when she's driving. Awesome. Okay, when I'm driving, I forget. Wait. Yeah. That's another thing. Like what Chris is saying, when you're driving, you forget that you're driving. And he's saying LOL, and I love that. Like he's like acknowledging that's like sort of funny. It's sort of a joke, but also like it is deadly serious if you really think about it. When you're driving, in a way, it's if you forget you're driving, okay, that's scary. Like, don't tell your husband or your wife or whatever. Like, we don't want to think that you forget that you're driving while you're driving. But on the other hand, I hope you do forget. If you literally thought about what you were doing literally while you were driving, that's scary. Look, I can't even stay on the topic. Can you imagine me operating a motor vehicle at like 65 miles an hour on the highway with a bunch of other motor vehicles? Like the only way I get away with, and I do drive, but the only way I get away with driving is like suspension of disbelief. No pun intended, right? Like, and again, with the airplanes, no one would ever get on an airplane if they really thought through what it was they were doing when they got on an airplane. It all relies on some sort of strange delusion that even when we're moving at 600 miles an hour, somehow we're just in a hotel room watching HBO, drinking drinks, right? Like, right? So how do we get away with that is really the question. Okay, I'm still looking. I get confused. Yeah, like how the flight attendants can walk on a plane. I'm with you. I mean, right when we now, and I will get. I promise we will get to a concept event. Oh my God. Okay, Siri totally thinks I'm yelling at her. I'm sorry. I guess I am. We will get to something like in notes, I promise. But one thing that Chris says in the chat, and then I'll move on. Yes, there is a different one when the airplane's taking off, or when the airplane is landing, or when the airplane is turning, when the airplane is doing anything other than cruising speed, which means constant velocity, right? Then all bets are off. Then that's different. Just like with the subway, when the subway's turning or slowing down, grinding to a halt, then we know something's going on, right? And there's a scientific reason for that. That's what we're getting at. But yes, we must make that distinction. You can be fooled apparently about motion as long as the motion is constant, as long as the velocity is constant. We have this whole question. If the velocity is not constant, if there is acceleration, then we're not as confused. And there's a reason for that. And we're getting to that. But if nothing else, actually, if you want a takeaway for right now at this point in the discussion, in the math part of this class, we've been talking about velocity, and then we got to acceleration. One big difference, and mathematically, you can say we've been talking about first derivative, and then we got to second derivative. If nothing else, part of this discussion is severely implying that there's a big physical difference between the first derivative and the second derivative. There is. Mathematically, they're both just derivatives. You could take the derivative of a function. You could take the derivative of the derivative of a function. You could take the derivative of the derivative of the derivative of a function. You can go on forever mathematically, and there's no distinction. It's just one of the same process over and over. But physically, what we're implying right now is, there's a difference between derivative number 1 and derivative number 2. Derivative number 2, you can definitely feel for reasons known as Newton's laws. But derivative number one, what we seem to be implying here is you don't feel it. You can be fooled about derivative number one. That's an important distinction that we're actually trying to lay down here. Okay, I'm going to keep going. Chat, and then I'll shut up. So yeah, when you take off, that's different. Or when the elevator, oh, the other example, sorry, I don't know if someone was going to mention, but elevator, classic example too, right? Like once the elevator's left, once the doors are closed and you're cruising between floor number 2 and floor number 9, like you better not feel it, right? I mean, right? I mean, you're just like a box. I mean, as far as you're concerned, the building is going past you and they're bringing floor 13 to you and opening the door, right? You could dribble a basketball in an elevator and you wouldn't have to adjust your dribble. Okay. I mean, I get that. Right. Okay. Oh, usually it's right. Okay. So like Amanda and Chris are saying in the chat, and I'm going to like, it is different when you take off. Absolutely. And that is definitely important. No question about it. What about? Yeah. And then someone just put in the direct chat, I won't mention names, but someone just put in the direct chat, what about when your ears pop? And I believe he or she is talking about elevators. 100% agreed. Your ears pop is an indication of something, but let me tell you, the ear pop only happens for one of two reasons, or maybe they mean an airplane. How does that play into this? Good question. With ears popping, which yes, can happen in really tall building elevators or can happen in airplanes. There's two scenarios where you're, and again, very good question. There's two scenarios where your ears would pop. One is if you are accelerating. If, the elevator starts speeding up or slowing down as it approaches a floor, but really more likely, if you're talking about the airplane, which is more frequently where ear popping occurs, the thing about ear popping is that's not about motion, actually. That is about altitude and air pressure. I mean, there's a whole other discussion, which we actually will get into in Physics 204, but just a quick, because that's such a legitimate question. Your ears respond to air pressure, and air pressure is lower at higher altitudes. Why? Because like the lower, like air near the surface of the earth, any bunch of air molecules in a layer near the surface of the earth have to hold up and support the weight of all the air molecules above them. I mean, it's that simple. It's like bricks in a brick house. The bottom layer of stuff has to support the weight of all the top layers of stuff. So as you go higher and higher in the air molecules are at lower pressure. They're just under less pressure. They're not forced together, packed together as tightly as you go higher. Your ears respond. Your ears are instruments that are designed to detect and measure air pressure, because ultimately that's what sound is. I mean, this is a whole other topic, and it's a big topic in Physics 204, but your ears are pressure instruments. So honestly, when your ears definitely do pop in airplanes, and that's a great point, but that has to do with how high, in other words, that has to do with changes in height, changes in air pressure. It doesn't have to do with the forward speed of the airplane. The airplane could be going any kind of speed forward or not, or doing whatever. But as the airplane is climbing through heights, you experience that in your ears. I don't know if that totally satisfies you. We could talk about it more in 204, but so atmospheric pressure, yes, that's what I'm talking about. Good, Amanda. So hopefully but it's a great point. All right, wait, so it's 3:54, so we have 20. Is there anybody else? I like what everybody's contributing to this. I just don't want to overlook anybody. I mean, of course, I'm going to say things, I promise. But is there anybody else in the room who just wanted to add or subtract anything from this discussion? Like, Yuyun, you're good, Yuyun? All right. Okay. She's like, yes, don't even call. Okay. All right, so who cares? Where am I going with this? Well, since I only have 25, I'm going to share a different screen now. I'm going to go back to my normal screen, because there is a point to all this. Well, here we go. Second. Hello. Come on. Siri is not even Siri. Mrs. Google is so sure that I'm talking to her, but I'm not. I'm talking to you guys. So it won't let me. She's like, what do you want? What I want Mrs. Google and Siri to take the exam. That's what I want. Okay, here we go. Okay. All right. So what it says here, I'll read it out loud. I'm going to go a little quick. Now I'm going to go a little quickly, okay, because I'm going to tell you what the point of all this is. And again, if it were up, we could discuss this forever on it, and people have. this whole concept, but I want to, give you a takeaway. So in terms of train of thought, first of all, it says up in blue, it's hard to read, but it says up in blue, it's a Gedanken experiment. Okay, I already defined that means thought experiment. Okay. So who cares? What's the purpose of it? Well, first of all, it says A, this thought experiment represents scenarios which actually do occur in our daily lives. It can be legitimately difficult to distinguish whether I move past you or you move past me. Like the first little thing that this discussion just established, as far as I'm concerned, is it literally can be a legitimate confusion. It is not, right? It's not just a matter of stupid people or narcotically affected people or something like that. It's like a legitimate confusion, whether I'm moving past you or you're moving past me. And I and you could mean anything, could mean a car and clouds, or a car and a moon, or a car and another car, whatever. All right. It's a legitimate confusion. That's point A. Point B. It's not just a confusion in our daily lives. Train of thought also represents a question of motion, which was authentically confusing and profoundly productive in history. Okay, this isn't just a day-to-day moment of confusion. This is actually this confusion of whether, sorry, I'm just trying to change the screen. This issue of whether we are moving or not actually goes broader than just you in an elevator or me on an airplane or whatever. I'm going to cut to the chase just because I think you guys have been discussing this so nicely already. I'm going to cut to the chase and say, look, that train that we're supposedly in this fictional example, we're sitting in this train and we're not sure if the train's moving past other things or other things are moving past it, or neither, if it's just sitting still, right? And eventually more information comes into play in the packet, right? Eventually we see these white lights, and we see the white lights all moving in a formation past us. So then some of us say like, oh, okay, that's the information I needed. Some of us say, oh, now that I see white lights moving past me, I guess it's pretty clear. Like I'm actually rushing through a subway station. Like, duh, if the lights are going to the west, then I must be in a train that's going to the east. But other people say, well, no, those white lights could be white lights like on another train. They could actually be passing you while you're sitting still, right? It's more information, but it doesn't necessarily resolve the whole question. Well, this is all an analogy to something that totally happened over centuries and centuries of history, and you all know about it from third grade, and maybe you even know where I'm about to go with this, and some of you even alluded to it in your examples, and that is to say, planet Earth, right? We're sitting on this rock. We look down on the floor and the floor seems stable to us. Like whether it's now in the year 2023 or 2000 years ago in ancient Athens or whatever, you look down on the ground and it is stable. You jump up from the ground and fall back down. You land in the same place you jumped up from, right? The ground doesn't slip out from under you. For example, birds don't have an easier time flying west than they do east. If you look down or you look at any of the evidence in your daily life on Earth, there is nothing to suggest at all. There's no sensory evidence to suggest that this rock beneath our feet would be moving through space. You look up and you see a sun rising in the east and moving to the west every day. If you look carefully at night, you see a whole bunch of constellations doing the same thing, rising in the east and moving to the west every night. If you look at the moon, you see the moon doing the same thing, all at different rates, but you see the moon rising in the east and setting in the west. So you look up and there's more information that definitely indicates some kind of motion. And the ancients looked up and studied the stars and studied the moons and studied the sun, and the planets very, very carefully and very intelligently and very precisely. And they came to the same conclusion that many, many people came to about the white lights in the train scenario, which is, okay, down below my feet, the ground is stable and not moving. And above me in the sky, everything is moving past me, right? People very reasonably, and very, in fact, brilliantly worked out a whole system with respect to which lights in the sky move past us while we sit stably still. But as you also know, as you know, from third grade or fifth grade or seventh grade or something, as you know, at some point, there was, well, at various points, there were various people who started either conjecturing or positing or maybe considering the possibility that we weren't sitting still in space, that in fact we could be moving past such objects as the sun and other stars, et cetera, right? And various people, Aristarchus in ancient Greece, Copernicus in Poland in the 16th century, and then eventually everybody's hero, or my hero anyway, Galileo in the 17th century. Galileo took very, very seriously this idea that had most recently been advanced or dealt with by Copernicus. He took very seriously this idea that the Earth could be moving past the sun. And he took it so seriously that many of us in third grade or sixth grade or seventh grade or something learned some kind of story that goes something like the following, and correct me if I'm wrong, but I learned some kind of story that went something like this. Okay, that went something like this. Like Galileo did not accept the idea that he should have blind faith and blind acceptance in the dogma. This is a story. This is not what I'm saying. I'm saying this is what I learned, or something like this. I learned that Galileo was a hero for rejecting the dogma of the church of the time, that Galileo, instead of just blindly accepting the idea that the Earth was sitting still in the center of the universe, Galileo had the guts to trust the evidence of his own senses and the faculty of his own reasoning. And he had the guts to develop this new thing called scientific method and scientific reasoning. And Galileo had the guts to reject authority and reject the blind acceptance of authority and go against that authority and actually say, no, my senses, the evidence of my senses and my logic tells me that it's possible that the Earth is actually moving past the sun rather than the other way around. And as you may have heard, Galileo got in huge trouble for this whole idea. He did get in huge trouble with the Inquisition, and he was eventually given a choice as to whether to take back everything he said and therefore live under house arrest for the rest of his life, which he did, or not take back what he said and be executed for it. Now, that part is true. That part is true. But the thing that's weird is if you learned anything, just raise your hand if you learned anything like what I just said, anything at all. Is this familiar at all? Thank you, Michelle. Okay, I'll take it. One person, good enough. Two people. Hi, you. Thank you. All right. And again, I'm exaggerating. I'm sort of simplifying. And of course, the story we get is simplified too. But here's the thing I'm trying to emphasize, that what I learned was that Galileo was a hero because he didn't accept blind authority. He trusted the faculty of his own senses and the faculty of his own reasoning, and thereby developed this whole great thing called the scientific method and experimental reasoning and science. And he said, okay, I actually think the Earth might be moving past the sun, not the other way around. Now, here's the thing. Galileo is my hero. Galileo is absolutely my hero. But my third grade teacher who taught me that is not my hero. Well, I find that story very, very disturbing and weird. And I spent a lot of my life trying to unravel it for myself, because here's the thing. All the evidence of my senses absolutely suggests that the Earth is sitting still. Nothing in my evidence suggests that the Earth is moving past the sun. Nothing in my evidence suggests that the floor is slipping below me. If I jump up, I land in the same spot, like we said a minute ago, right? And you might say, well, yeah, but the Earth is moving so slowly, like you could barely notice it. Oh, no. If you, like me, build a solar system model that I was asked to build in third grade from a bunch of fruits, right? Like make a watermelon represent the sun, and make a tangerine or something represent the Earth, and have the tangerine go around the watermelon, which was the correct thing that I was supposed to do. In that model that I accepted in third grade, the Earth is not just dribbling past the sun. If you look it up on the web, right now, if you feel like it, the speed at which the Earth supposedly moves past the sun is 65,000 miles per hour. That is way faster than any airplane any of us has ever been in. That is faster than a rocket needs to go in order to escape the Earth's gravitational field and go to the moon. Rockets only have to go 45,000 miles per hour to get to the moon. We're claiming, if you accept this theory, which I'm not saying you shouldn't, but if you accept this idea that the Earth is moving past the sun, then you're accepting the idea that the Earth is moving past the sun at 65,000 miles an hour. And furthermore, you're accepting the idea that, at least in modern science, that the sun itself is not even still. It's going past the center of the galaxy at 650,000 miles per hour. Where I'm going with this is this. I'm not saying Galileo was wrong. I love Galileo. But let's be very careful. Like, if Galileo was a hero because he rejected blind, like the acceptance of blind dogma and blind authority, and he went with the faculty of, and he trusted his own senses and his own reasoning, then when I just built a solar system in 3rd grade and accepted that my teacher told me that the Earth moves past the sun, I was just accepting my teacher's blind dogma as far as I'm concerned. Like, I had no reason. I don't remember ever asking my teacher, wait a second, if the Earth is moving at 65,000 miles an hour, how come we don't fall off? Or how come we don't feel, or how come we don't feel it? Or how come I can jump up and land in the same spot? Like, maybe some of you did ask that, and I hope you did. I didn't. I just accepted that Galileo was a hero because he didn't accept authority, and I just accepted his authority. And it's no wonder that I got turned off by science for a number of years before I came back to it, because it seemed to me at that time that science was just, okay, the Earth is moving. It doesn't make any sense, but just accept it. The Earth is moving at 65,000 miles an hour. Go on your way, little boy. I'm here to say that what Galileo did was Galileo advanced a principle. Galileo's first task was not just to prove to people that the Earth is actually moving. You can't actually do that. The first thing Galileo had to do was convince people that whether or not the Earth was moving past the sun, we wouldn't be able to tell the difference. That's the first point. In other words, Galileo, in a number of books that he wrote and that he got into major trouble for in approximately 1626 AD, Galileo advanced a principle called the principle of relativity, which he wrote down many, many different ways. I mean, none of which are in English the way he wrote them. We're going to do it in English, obviously. But even in the languages in which he wrote, both Italian and Latin, on purpose to reach a wide audience, he wrote this principle down in many different forms. We're going to hear 3 of them quickly today, and we're going to hear the rest of the 6 over the course of the semester. And everything in physics comes back to these different forms of the one and same idea. What I'm trying to say right now, and I know I'm talking a little bit quickly now, but I'm trying to say you got assigned this packet early in the semester for a reason. We didn't talk about it until a little bit later in the semester, also for a reason. But I want you to know that this idea, this principle of relativity, doesn't come from physics. Physics comes from it. This principle of relativity is deeper than a law. It's the birthplace of laws. Just like in the United States, New York State can make a law, or New York City can make a law that affects your behavior, but New York State or New York City cannot, well, New York State cannot make a law that violates the United States Constitution. You know what I'm saying? The United States Constitution doesn't tell you what you can do. It tells New York State and courts and blah, 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 what laws they can pass. Same thing here in physics. This is why step 3 of the problem-solving method, step 3 is general definitions and principles. A principle is deeper than a law. This principle that Galileo, the first form of the principle that Galileo advances in order to defend this crazy idea that the Earth could possibly be moving past the sun at 65,000 miles an hour while none of us feel it or sense it or take it into account in any way in our daily motions, is Galileo basically says, look, if it were a boat, which you've all been on, or in modern terms, we would say a car or an airplane or an elevator, but Galileo has this whole thing where he's like, look, if it was a boat and you went down to and you anchored the boat and you went down to the cabin of the boat and did a bunch of things, like had to look at a goldfish going around in a tank and like dropped a ball on the floor and did a whole bunch of little things in a cabin in the bottom of the boat, and you watched how all of your little gestures played out, and then you let the boat set sail, you pulled up the anchor and you let the boat start sailing at big speeds, and you went down to the cabin, you'd have all the same experiences again, right? Just like all of you were just arguing, right? He's saying that's not because you're crazy. That's not because you're missing something. You can't tell whether the boat is moving or not for this reason. And for the same reason that you couldn't tell whether the earth was moving or not. The reason is this: Form 1 of Galileo's principle of relativity in English says the laws of physics, whatever they are, whatever they're going to be, the laws of physics are the same. This says same, can't even read it, sorry. Are the same in all inertial reference frames. Now, I'll explain what I mean by an inertial reference frame on the next page. In fact, I will turn the page. But in short, it means at all different velocities. I'm going to turn the page right now. Galileo first says, now remember, again, this is the beginning of physics, the beginning of what we call classical physics. This is literally before we have any laws at all, before we have, notice even in this class, we've been in this class for a month already. I've given you equations, but those equations are just definitions, right? All we've done is define our terms. We haven't established one freaking law yet at all. You may have heard of Newton's laws in high school. Of course, they're super important in physics, but they come later. They come 100 years later, and they come later in the course for a reason. Before we even get to laws, we have a man named Galileo who says, whatever the laws are going to be that we're going to discover, whatever laws I'm going to figure out, whatever laws are going to come after me in future generations, whatever they are, they're got to be the laws of motion. And they can't change from one motion to the next any more than a law of the land can't change from one citizen or circumstance to the next. Laws dictate circumstances. Circumstances don't dictate laws. So Galileo says, so I just rewrote it here. It's the same thing, right? Form number 1, the laws of physics are the same in all inertial reference frames. What does that mean in English? Well, inertial means unaccelerated. So this is like a way of getting back to what you guys were already saying, like when the airplane's taking off or speeding up or slowing down or turning, those are all changes in velocities. So that's a different situation, which we'll get to. But inertial means unaccelerated. As long as we're in a reference frame that is unaccelerated, the laws cannot change from one velocity to another. What do I mean by a reference frame? It says right here, a reference frame is a perspective. More specific, just like you have perspectives in video games, right? You have third-person perspective, first-person. A perspective is how you view the world. In science, more specifically, more mathematically, more rigorously, a reference frame is a coordinate system. It's a grid. Also true in many video games. It's a grid through which we view the world, right? Specifically, though, of reference, and we're going to get, believe me, I know I'm talking fast right now. We're going to expand all of this over time in the class. But a reference frame specifically is a coordinate system maintained by someone or by an observer who is regarded to be stationary, regarded to be at rest. Again, if you play video games at all, I think, or look, if you watch movies or if you've ever been in a car, it's kind of like what Chris was saying. When you're driving a car, right, the way the world feels, your perspective, your reference frame is that you are still and the world is going by you, right? That's how you experience it. Now, part of your brain may say that's not what's really happening. We'll get to that in a minute. But the way you experience it is you are stationary. The world is moving past you. That is called a reference frame, okay? A perspective held by someone who regards themselves or who is regarded to be stationary, like whether or not that's actually true. So what we're saying right here, and I know I have 6 minutes, and I know I'm talking loud and fast. Again, we'll expand all of this all forever in the rest of the physics course. But what we're saying here in form number 1, sorry, in form number 1, we're saying, in English, what we're really saying is, in all different velocities, it doesn't matter what speed you're going, the laws of physics have to be the same. The laws of physics can't change just because someone's going 600 miles an hour. Different speeds are the circumstances of the laws. The laws don't bend around speeds. Speeds occur due to the laws, right? So the laws are the same no matter what speed and direction you're going. That's what we're saying here. Now, hopefully, I'm going to move on in a second. Hopefully, if you're following me at all, you might be thinking something like, okay, I get that, but I don't see why that's a big deal. Like, obviously, the laws are always the laws. If you're thinking anything like, yes, I get this, but it seems obvious, good, because this is the way physics is supposed to work. It's supposed to start with an intuition that we all agree on. So the first thing Galileo is saying is, look, I don't even know what the laws are yet. Let's take an example of something I sort of know, like gravity. I don't know all the details of, I'm Galileo, I'm you, I'm me. I don't know all the details of gravity, but basically I know that if I drop something, it falls down in a straight line and lands at a target right below my hand. Like, let's assume that's the law of gravity or some rough version of it. What Galileo is saying is whatever that law is of gravity, whatever the details are, it can't change from one speed to the next. It's got to be true whatever speed you're going if it's a law. If you think that's obvious, good. I agree with you. It's meant to be somewhat self-evident. It's just basically saying laws are laws, whatever they are. But then if you go to form number 2, here's form number 2, and I know we have 4 minutes. Form number 2 is a different way of saying the same idea. Actually, it's an extension or an implication of the same idea. If form number 1 is true, then form number 2 must logically follow. And form number 2 says no experiment could ever be designed or performed to measure the absolute velocity of a solitary object, like through space. What do I mean by that? I'm saying, okay, if the laws are, say you're on an airplane and you wake up mid-flight, like it's been flying for a while, it's like going to Japan, it's going over the ocean, blah, blah, blah. It's dark outside. So you wake up and you're like, wait, are we there yet? I don't even know. Like, are we flying? What's going on? I can't tell, it's dark. So you decide, all right, I'll do a simple experiment. I'll be scientific about this. So I'll do something straightforward. Like I'll drop a pack of peanuts on the floor because I don't have to be like an elaborate scientist to do this. I know that if I were in a parking lot, if the plane were stationary and I dropped a pack of peanuts, they would fall in a straight line and land on the floor right below my hand. That's what would happen if the plane were stationary. So I think I'll drop a bunch of peanuts, and then if they land directly below my hand, I'll say to myself, oh, I guess we must be there. We must be parked. But of course, if you're all with me, if you're all following the logic of this, if you all just noted GPR form number 1, you realize, well, wait a second, that experiment's not going to work, because whether we're moving or not, whether we're moving at 0 miles per hour past the Earth or 500 miles per hour past the Earth, either way, the laws are the same. So the experiment must work out the same no matter what. If I drop my peanuts, as long as I'm going at a constant velocity, my peanuts are going to land on the floor. In fact, that's why I'm willing to get on the airplane in the first place, because I trust that all the laws of physics are going to work in an airplane the same way they work on the ground, even though I'm going 500 miles an hour in the airplane. But what that means, and if you really take that seriously, if you take it seriously that the laws of physics are the same at 500 miles an hour as they are on the ground, then that means it's not just a confusion. You literally cannot even design, let alone perform any experiment. Doesn't matter the technology. Does not matter how advanced technology is. You cannot conceive of an experiment that would resolve the issue of whether you're moving past the clouds or the clouds are moving past you. Like there's relative motion, yes, you could observe. But whether you're actually still, or the other thing is actually still, there is not an experiment that you could ever do to resolve that. We've got 2 more minutes. Now, Galileo is the guy that comes along and says, from here on in, there's a difference between physics and philosophy. And the difference is from here on in, for the first time in history, and the difference is that physics derives its truths from reproducible controlled experiments that involve data collection, right? Galileo is the daddy of the scientific method of experimental arbitrations of truth. So Galileo says you cannot do an experiment to decide whether the airplane's going past the clouds or the clouds are going, or in the original, I think it was Marilyn's example or someone's, you can't actually do an experiment to actually decide whether the truck next to you is going backwards or you're going forwards. There isn't an experiment that can actually resolve that. Therefore, our final point for today, GPR form number 3, if you literally could never do an experiment to resolve what one object is actually doing, I mean, that's what we're saying. we're saying you can always know that one object has motion relative to another, but whether one is actually by itself going 0 or some number, you cannot determine that in an experiment because the laws are always the same at all speeds. Therefore, form number 3, in short, in English says, then if you can't find it in an experiment, it's meaningless in science. So from here on in, the principle of relativity says, in short, every velocity is relative. Every velocity is a relation between two objects. There is no such thing as the velocity of an object. From here on in physics, what I'm saying is to talk about whether the airplane is actually moving or not is BS. That is meaningless in physics from here on in. You could talk about whether the plane is moving relative to the clouds, but you could say the plane is moving at 20 miles an hour. You could say that the plane is moving 200 miles per hour east past the clouds, or you could say that the clouds are moving at 200 miles per hour west past the plane. And both statements are true from both perspectives, and both perspectives are equally legitimate. As long as something is not accelerated, all perspectives are equally legitimate in physics. No speed applies to just one object, and no direction either. All velocities are from here on in necessarily comparisons of one object to another. There is no meaning to the velocity of one object by itself. That is the principle of relativity. It becomes very mathematical, as you will see next week. But that's the first 3 forms right there. And this is what starts the physics machine, is this recognition of how Earth could move at 65,000 miles per hour past the sun without us ever feeling it. Okay, I went one more. So that's it. So I'll see you Wednesday. Yeah, I'll see you Wednesday. I will hang out for a second if there's any questions, but other than that, thank you for being so patient, and I hope it made sense. Bye. Yes, bye. Exactly. But I will hang out and I'll turn off the recording. Have a good day. Thank you. I will turn off the recording.
Thank you, Professor. Goodbye.
Thank you. Goodbye. Awesome. Thank you. Thank you. Thank you, guys. Thank you. Okay, I'm turning off the recording.